Hello everyone, I'm Jeffrey,
And I'm Matt.
and today we'll be continuing our series on binary exploitation with an introduction to ROP attacks. So we'll be discussing what an ROP attack is, why we would use it in place of other techniques such as a normal buffer overflow, and how to do it. So let's get some quick review in first. This is the typical memory layout that hopefully everyone is aware of by now. It is week 5. Important things to note here are the stack, because when we do any kind of buffer overflow, we're basically saying the stack is our property now. And we want to be able to know what is in the stack. So let's look at a typical stack frame for, let's just say, a function foo. So let's say that this function foo reads from standard input into a buffer. So we can see that buffer grows this way in memory. But wait, you may ask, that doesn't make a lot of sense. I thought the stack goes downward. Well, the thing is, it does. But if you think about it like this, buff plus I times k, right? You have to have it so that when you look through your memory, you go up because of how addressing works. So that's the buffer. It's important to know that the buffer goes up. The next important things are the local variables, because it'll get in the way when you're trying to do a buffer overflow. You'll forget about them, and then you won't realize why the return address isn't being changed. And the other thing to note are the pointers to the last frame. So this is like the stuff with push RBX or push RBP, basically any kind of push that adds things to the stack in order to keep track of it. I believe it's callee saved, those kinds of registers that get pushed onto the stack. And then finally, we have the return address. This is our holy grail. We must change this in order to have an overflow, because without this, we can't change the flow of the program. Might as well not even have an overflow in the first place. So once again, our goal is to, in a normal buffer overflow, is to overflow our buffer all the way up here. Remember that if we have some unsafe functions such as gets or string copy, it won't check for the size of the buffer, so it will just keep reading, and it will keep placing all of this data in here. So basically, you can overwrite all this memory here and use it to your liking. So in a normal buffer overflow, what we are doing is that we are overwriting this memory with our own shellcode. So this would be the old RIP. This would be where the old pointer would have gone. So when we would have reached an RET at the end of our foo, we would have, if this wasn't changed, we would have gone back to, say, main, right? But since we overrode it, now we can point it to wherever in our stack, and we can just nope slide all the way to our shellcode and execute it. This is really nice for doing basically everything, and it's why buffer overflow is really powerful. However, there is a thing that prevents buffer overflow shellcode from being run. What if we just mark this part of, because we know where the stack is in memory, what if we just mark this as non-executable? That way, we don't have to deal with buffer overflow, even if we mess up, and then we add a buffer overflow here and there. What happens then? How can we still break the program? Here's where ROP comes in.
All right, so ROP is a class of attacks that gets around the no exec on the stack. So there's a specific portion in memory that's laid out that is executable, right? And that's where your binary is loaded when you go to execute the binary. So the theory behind an ROP attack is if we can overwrite that instruction pointer to point to somewhere within that executable memory, then we can force the computer to execute code that we want as long as it's already loaded in an executable portion of memory. So the simplest form of this is kind of a special case of an ROP attack. It's called return to libc. Libc is the main C library. It's got stuff like stdio, and that has a lot of really useful function calls. For example, if you were trying to get root access on a system, there is a function call in libc that's just called system, and you can pass that an argument like /bin/sh, and that will give you a terminal on the system. So if we can overwrite that instruction pointer to point to where system is, and we can call it with the /bin/sh argument, then that'll complete our ROP attack. Now, the reason it's called an ROP attack is because that stands for return-oriented programming. So the main thing we're focusing on is return statements. And those return statements form what we call gadgets within a binary. They're called gadgets because it's like really small things that we string together to form a larger program. So you might wonder why we don't just always use return to libc, and the reason is most modern computers implement something called ASLR, which is address space resolution, address space layout randomness. Sorry, and that actually randomizes the space in memory where libraries are located. So every time you run the binary, for example, libc will be located somewhere else, and so it's really hard to predict where libc is going to be located, so we're not quite sure where to overwrite that instruction pointer to. But if you have gadgets within the binary itself, then those gadgets will always be located at a distinct offset from the rest of the binary, because the binary is always laid out the same way in memory. So if you can get one memory address within the binary, then you can use that offset to calculate the memory address of gadgets. So using gadgets is harder than just returning directly to libc, but it is more useful when there are those protection mechanisms in place. So on this walkthrough doc here, we can see a short explanation of what a gadget is. And of course, gadgets center on the ret instruction, which is the byte value C3. So there are some really useful tools you can use to find gadgets. One of them is ROP gadget. It's available on GitHub. It's written in Python, and that will search for a bunch of different gadgets that you can use within a binary. So basically, how an ROP attack works is it's just like a buffer overflow, except instead of pointing the return instruction pointer to code that we've written on the stack, we're actually going to point it to a series of gadgets. And so we're going to chain gadgets together to eventually form the whole program that you want to do. And it's programming because you still have to combine the gadgets together. So it's still writing a program. It's just with a much more limited subset of what you can do, because it's limited by what gadgets you have available in the program.
Think of it kind of like this. A buffer overflow, a normal buffer overflow, is basically you saying, go to my code in the buffer. A ret to libc is basically saying, go to this function in libc and like execute it with the parameters I set. And an ROP attack is basically you reconstructing programs with gadgets. So with gadgets individually, it's a lot more trickier, and then you have to chain them together to accomplish a lot of tasks. But like ultimately, ROP is fairly powerful, and it gets around DEP. So we will get into it a little bit later if you're still unclear about how ROP works. But first, we'll have our demo. Alright, so here I have my Protostar VM running. Protostar is from Exploit Education. It's really nice. Protostar is basically just it's a disk image that contains various challenges for smashing the stack for fun and profit, and everything else in between. So, if you have free time, download it here. Anyway, let's get into the demonstration. So we can see that currently I am user, and we'd like to change that because we're hackers. We like to gain access to root, so we get all the power. So let's look at a way to do that through stack 6. So we're given the source code for this challenge. We have this function getPath, and we have a main function, obviously, that calls it. So we can see that it has a buffer overflow because it uses gets. Remember, do not use gets if you're not making a buffer overflow challenge. Just don't. Anyway, so there's a few interesting things in this source code. There's this ret equals to built-in return address thing. That's pretty interesting. And so what this does is that it basically gives you what is in RSP, like what's on the top of the stack, and it returns it to you. So basically, this is checking if ret and bf0000 equals to bf0000. So it's checking if this return address on the stack is equal to this. So what kinds of return addresses would have these upper bits? Well, I'm sure you can guess, but we can see this directly through GDB. So let's GDB stack 6 and see. So through GDB, we can start it to load in the file and all the symbols, and then we can do info proc mappings. And through this, we can see the start and end addresses of pretty much everything here. So like this is our source file, or this is the binary file, and then this is libc, and then this is the stack. And we can see that all the addresses that start with bf are on the stack. So this is basically just discount DEP. This is preventing us from writing a normal buffer overflow, especially because this exit function right here, it just unconditionally exits. It doesn't use a return or anything like that. So we cannot do anything. We cannot do any kind of code execution on the stack. But we still have a buffer overflow. So what can we do? Well, there's this exploit called ret to libc right here. And so ret to libc allows us to execute code in libc. And so the way we do that is, like always, by manipulating the stack. So let's see how we can do it. So first, let's just say we want to run a shell as root, because well, this program is a setUID program. So that means that it's run at the level of the person who made it, and in this case it would be root. So basically, if we were able to run a shell in this with the creator's permissions, we would be able to run a shell as root, which is our goal. So let's see, there's several ways about doing this. One way we could do it is by finding out where system is. And so system is a that's in GDB, sorry. But system is basically a C function that executes a command specified by calling this, and it returns after the command has been completed. So basically, it executes a shell command, whatever you want to do, and then sh is basically just the shell. So you want to execute a shell. Going back to GDB, we can find the location of these things. So let's start to break it main automatically, and then let's look at where system is. So we see that system is at this location in memory, and because we don't have ASLR turned on, we can reliably use that. We won't have to find an offset or anything. So that's a nice and dandy. But how are we going to find bin/sh, what we want to run system with, or the argument for it? Well, in 32-bit systems, it basically takes the arguments off of the stack instead of using those extra registers such as RDI and RSI. So we can just directly put a pointer to bin sh on the stack, assuming that we find a string bin sh somewhere in this program. Now, because this is a challenge and everything, I assume that you think that there is a bin sh. So let's try thinking of ways we can find it. One of the ways we can is by gdb find, and we can look at several locations. So let's do actually do infoproc mappings first to look at memory addresses again, and then let's look through these through the find command. So the find for find, you have a starting address and like an end. You have a starting address and an end address, and then you look for a certain set of bytes. So let's just say we want to look in libc. And then we want to just look for through like all of libc. And then we want to look for bin sh. Did I do this wrong? Maybe not enough 9s, that might be the issue. There we go. Alright, so we see that there is a location in memory that has bin /sh according to GDB. Well, the funny thing is, let's first look at that memory location, and then let's discuss it afterward. Funny thing is, it's not actually /bin/sh, and that's kind of weird because you would think that GDB would work properly like it's supposed to, but the thing is, remember that you are not the master of the stack. You're merely trying to use the stack as a vessel, but you do not control the stack entirely. That means that like you can't really trust the stack to always have it at the exact location. So instead, let's try finding out where bin sh is through its offset. So let's run a command. Let me see if I remember this correctly. So we can use the command strings to print out the printable strings of a file, -a for everything, and -t for offset. And then we want to look for /tx for offset. So, and then we want to look through libc. So libc in this situation would be your xb7. Wait, and we can just do /lib. Yeah. Because we're looking through the file for this. And then this basically gives us all the strings in libc and their offsets. And then we can grep through, oh god, I meant to grep through that. Okay, that's fine. Okay, you know what, I'll just gdb stack 6, and then let's get the thing again. Alright. Sorry about that. Alright, so we can grep through that for /bin/sh. And we find this offset. Yay! So what does this offset do? So we can use this offset to basically calculate the location of bin/sh. And we already know the location of libc, right? So that means we can easily calculate the location of bin/sh. Let's do this in GDB. And let's examine the string at first let's get the info proc mappings. And then let's examine the string at, let's see, 0x B7E9 700 plus our offset, so it was 0x. I have it written down somewhere. I guess not. Wait, let me just. Man, it's so annoying that this doesn't copy and paste properly. All right. All right. Let's do this properly this time. All right. So this offset, wrong one. And then we do GDB on stack 6. And then we get the location of we get the location of libc in memory, and then let's examine the string there at this location of memory plus the offset. So our offset is 11F3BF. I forgot to add the OX. There we go, and we found bin sh successfully. Alright, that's basically the two major components of our code, and we can basically use this to create an exploit generator in Python. So let's look at my exploit.py. So I have this myexploit.py already done. Or I have this demo.py that I've done. And then it has all these locations that I can put in for this buffer overflow, or this ROP attack. So we already know the system location and the bin sh location. And all we need to know now is the amount of bits we need to basically reach the EIP. So we need to find that out, and we can find this out pretty easily through either a brute force or by just looking at the source code. And we also need to have this extra trash data because we need to properly set up the stack such that the bin sh location is in the right location. So let's first find out our offset. So if we do this, we can go to disassemble main, or yeah, disassemble main, or start. This is excuse me. Okay, let's just go there, and then oh, that's why. All right, so we go disassemble main, and then remember that it's in get path, and then disassemble path, get path. We can see that there is allocated space onto the stack. Oh, it's near the top, but we can see that we subtract 68 in hex from the stack pointer. So the one loaded for gets is the one that's, wait, yeah, this one, sorry. So this is the one minus x 4c. So 4c is 4 times 16. There's 64 plus c, which is 12. So that's 76 bytes. So let's try it with 76 bytes then. Let's try running it and then inputting 76 bytes. So okay, let me just, okay. Well, the thing is, it won't work because there's also, if you noticed earlier, there's also push onto the stack. So that means our EIP that we want to reach is also behind an EBP. So that's because it's a 32-bit system, that means there's an extra 4 bytes that we have to overflow. So in total, we have to overflow 80 bytes.
So that's an interesting point. If you saw the source code earlier, when Jeffrey had it up, you saw that buffer was only 64 bytes long in the actual source code. But you'll notice right now that we are overwriting 80 bytes. So that's something that the compiler is changing. So even if you have the source code, you might look at it and say, okay, buffer's only 64 bytes, so I only need to overwrite that, and then I'm on the stack. But that's not actually the case in this case and in many demos that you might run into. So it's always good to actually examine it in GDB and look at what memory address is being called when you're calling that vulnerable function and how many bytes you need to overwrite.
All right, so back to our exploit code. We can look in our exploit.py, and then we can see that this is the actual payload that I made. So we can see that we have this offset correctly. So we have 80 bytes because each character is a byte. And then we use this Python module struct, which is in Python 2. And then what this struct module does is that it correctly structures our locations in memory that we have found, such as our system and our bin.sh. And it correctly formats it in a way such that we are able to put it into little endian format into our input because, well, first of all, it is, if you put it in this form, it won't be correctly formatted. Second of all, it won't be in the right order. So, and then notice how we have this extra like exit code that's just trash to format the stack correctly. We can actually see this in our memory if we look at GDB with it. So let's just GDB stack 6, and then give it our. First, let's find a return for get path, and then break there, and then give it our exploit. Oh, sorry, forgot the. There you go. So we can see that we gave it all this. You can kind of see where our code is. It's like in these random characters here, and then you can see that this is our trash data. So let's examine what we've done to the stack. So first of all, we can note that EBP has been successfully overridden by A's because A in hex is 0x41. And then secondly, we can note that if we examine the bytes at the stack, we have successfully overridden it with our code. This is the 4 A's for trash, or our random trash. And then this is our location memory for system. That's location memory for system right there. 7B or B7 EC FF B0. And then this is our location memory for bin.sh. B7 FB63 BF. And then you can kind of see why the 4 A's was necessary, because we had to format it in that so that the stack would be properly formatted, so it would get this, because otherwise it would be over here, and then it would only take when we returned when we do return, we would only just go here and then remove all this extra stuff, which would have included our bin.sh. So this will correctly work, and we will go into the system. And so let's demonstrate this by just running the program. So let's so in the end, if we have our correctly generated exploit.txt, we can cat it out, use this dash command to tell the shell command to tell the shell command that we haven't said all we had. We haven't closed off standard in, and then we can pipe that into stack.c or stack6. And now we can see that the program's hanging. And who am I? I'm root. We have successfully became root. And now we can be Hackerman. And notice how there's two shells running here, and that's because we have the shell that we're in, and then the sort of child shell that we've generated in this stack C, or stack 6. And that's basically it. And then notice if you exit, there's a segmentation fault, because we literally just destroyed the stack. And we haven't formatted the rest of it correctly. That's basically everything for this demo.
All right. Make sure you join our office hours later if you have any questions. The challenges should be up. We only have a couple because these are a lot more difficult than some of the other challenges. And of course, as always, if you need help with this or potentially with Attack Lab for CS33, if you're in that class, then make sure to join our Discord and ask questions there. Thank you, guys.
All right, thank you.